Episode 17, Einstein's Impossible Idea. At the end of the 19th century, physics found itself in an unexpected crisis. For more than 200 years, Isaac Newton's picture of the universe had seemed almost perfect. Space stretched endlessly in all directions, fixed and immutable, while time flowed steadily onwards like an invisible river, carrying every event in the universe along with it. No matter where an observer stood, no matter how fast they traveled, everyone was assumed to share the same universal clock. It was an elegant and comforting view of reality, and one that had explained the motions of planets, comets, and falling objects with astonishing success. Yet light refused to cooperate. Experiments had repeatedly shown that the speed of light was always the same, regardless of the Earth's motion through space. The Michelson-Morley experiment had searched for evidence of the Earth's movement through the mysterious ether and found absolutely nothing. The result was deeply unsettling. If the Earth really orbited the Sun at nearly 30 kilometers every second, then why could this motion not be detected? Why did light appear completely indifferent to the observer's movement? Several brilliant physicists attempted to rescue the old ideas. George Fitzgerald suggested that objects physically contracted in the direction of their travel. Hendrik Lorentz developed the mathematics further, demonstrating that moving bodies and even moving clocks would appear altered in just the right way to explain the missing ether wind. Henri Poincaré suspected that perhaps the laws of physics should look identical for everyone traveling at a constant speed. He was remarkably close to the truth, yet even he hesitated at the final hurdle. Like almost everyone else, he could not bring himself to abandon Newton's concept of absolute time. At the same time, another problem was troubling scientists. 40 years earlier, James Clerk Maxwell had brought together electricity and magnetism into a single elegant theory. Maxwell's equations successfully described radio waves, electromagnetic fields, and light itself. But hidden within these equations was a remarkable prediction. They implied that electromagnetic waves should travel at one fixed speed, approximately 300,000 kilometers every second. The equations made no allowance for the motion of the observer. They did not suggest that someone moving towards a beam of light should measure a different speed from someone moving away from it. Light seemed to possess a preferred speed, built into the laws of nature themselves. Most physicists regarded this as a mathematical curiosity, expecting that a better understanding of the ether would eventually explain everything. But one young man began to wonder whether the equations should be taken seriously. Albert Einstein was not a professor, nor did he possess a well-equipped laboratory. At the age of 26, he worked in the Swiss Patent Office in Bern, examining applications for electrical inventions and judging whether they were genuinely original. It was not glamorous work, but it gave him something precious: time to think. Einstein had a habit of exploring physics by constructing vivid mental pictures rather than immediately turning to mathematics. Since his teenage years, he had been fascinated by light, and he often imagined impossible situations to see where they might lead. One question had stayed with him since the age of 16. What would happen if he could chase a beam of light? Suppose he traveled alongside it at exactly the same speed. Would the wave appear frozen beside him, hanging motionless in space like a ripple trapped on the surface of a pond? According to Maxwell's equations, this was impossible. Electromagnetic waves could not stand still. Yet according to Newtonian ideas about motion, there seemed no reason why such a thing should not happen. Einstein slowly realized that perhaps physicists had been trying to save the wrong part of the theory. Instead of inventing ever more complicated explanations for why light always appeared to travel at the same speed, perhaps they should simply accept that this was a fundamental property of nature. Perhaps every observer, regardless of how quickly they moved, would always measure exactly the same speed for light. It was a breathtaking suggestion, because if the speed of light remained unchanged for everyone, then something else had to change. Einstein understood that the casualty would not be light itself, but time. To illustrate the problem, Einstein imagined a long railway embankment with an observer standing exactly halfway between its ends. Two bolts of lightning strike the embankment simultaneously, one at each end. The observer standing on the embankment sees the flashes arrive together and concludes that the lightning strikes happened at the same moment. Now, imagine a passenger seated halfway along a train moving rapidly in one direction. As the flashes travel towards the passenger, the train moves closer to one flash and farther away from the other. Since light travels at the same speed for everyone, the passenger receives one flash before the other and concludes that the strikes did not occur simultaneously. Both observers are correct. The astonishing implication was that there is no universal now. Events that occur at the same moment for one observer may happen at different moments for another observer moving relative to them. The universe no longer possessed a single master clock ticking away in the background. Instead, each observer carried their own measure of time, and two people moving differently through space could genuinely experience different sequences of events. When Einstein published his paper in 1905, many physicists struggled to accept the consequences. Some believed he had merely invented a clever mathematical trick. Others thought the conclusions were absurd. The suggestion that moving clocks could genuinely tick more slowly than stationary ones seemed impossible to reconcile with everyday experience. Yet Einstein's theory explained every experiment. It removed the need for the ether, explained the Michelson-Morley result, and transformed Lorentz's mathematical corrections into something profoundly physical. Time itself was no longer absolute. It could stretch, shrink, and flow differently depending upon an observer's motion. One scientist immediately recognized the importance of Einstein's work. Max Planck, already famous for introducing the quantum idea, became one of Einstein's earliest supporters and helped ensure that these revolutionary ideas reached a wider audience. Within a few decades, experiments would prove Einstein right beyond any doubt. But before that happened, physicists first had to confront a startling possibility. If two identical clocks followed different paths through the universe and later reunited, would they still agree on the amount of time that had passed? In the next episode, we shall discover that they do not. Time itself can slow down, and Einstein's impossible idea turns out not to be philosophy, but measurable reality. Thank you for watching and listening. If you've enjoyed traveling through time with me, please like and subscribe. And if the next episode is available, click on it now and let's continue the journey together.